Hi, everyone. Hope you can hear me. Okay. Hi, I'm Yamini. I'm part of OpenVino architecture team. And today, my colleague Mayuresh and I will talk about how we optimize ONNX models with OpenVino. First, I'll talk about how we optimize ONNX with native OpenVino. And then Mayuresh will talk about ONNX Runtime OpenVino execution provider. Okay, OpenVino is an open source toolkit for optimizing AI inference on a variety of heterogeneous devices, like Intel CPUs with AVX2, AVX512, AMX support, and Intel integrated and discrete GPUs, as well as Intel NPUs, like the ones that you see in Meteor Lake and Lunar Lake Core Ultra AI PCs. And we also have support for different model formats, like ONNX, PyTorch, JAX, TensorFlow, TensorFlow Lite, Paddle, and GGUF. But in this presentation, we will focus primarily on the ONNX support with OpenVino. And OpenVino provides several optimizations. We have graph-level, high-level optimizations that are target-independent, and we also have low-level optimizations that are target-dependent, that we compile for specified hardware. And we also have optimizations at the lowest level, at kernel level, that we provide with 1DNN on Intel CPUs and GPUs, and we have our own custom NPU library for optimized performance on NPUs. And apart from that, we also have Neural Network Compression Framework, or NNCF, where we have support for post-training quantization and quantization-aware training techniques. And we also have a high-performance GenAI library that we use to support end-to-end GenAI pipeline optimization. Now let me walk through how we support and optimize ONNX models with OpenVino. So even before the models hit the runtime, we use Neural Network Compression Framework, or NNCF, to quantize or compress the model. So NNCF actually supports a variety of techniques like quantization, weight compression, and pruning. And we have support for low-precision data types, including int8, fp8, and nf4, int4. And we're also working on mixed precision data types, where we can strike the balance between performance, memory, and accuracy. So we can actually have some of the layers in FP16 or bfloat16, which are sensitive, and we can also use int4 or int8 quantization for other layers. And we also support pre-quantized ONNX models that are quantized with tools in the ONNX ecosystem, as well as the full precision ONNX models from FP32 or FP16 format. And after optionally quantizing the model, we convert the ONNX model to OpenVino IR using a module called ONNX Framework Frontend. As part of this conversion, we also apply high-level graph optimizations, including node fusions, removal of redundant nodes, loop unrolling, constant folding, and many more. Once the IR is converted, then we compile to the specified hardware target, like GPU or NPU. And on-device compile is a widely used feature today in OpenVino, but we are also looking at ahead of time compile, trying to support more remote compile features, and looking into aspects like weight sharing and weight-free blob compilation to reduce the disk space when we compile the models. So after the compilation, then we have OpenVino runtime, which uses a variety of hardware plugins like CPU plugin, GPU plugin, and NPU plugin. And we also have a virtual plugin or meta plugin called Auto that can automatically select the device based on aspects like device priority, resource availability, or even user-defined performance hints like latency mode, throughput mode, etc. So let me walk through the model preparation and optimization in more detail. This slide shows a code snippet of how to use an ONNX model and convert it to OpenVino model and then compile it to the specified target device. So first, we provide the ONNX model to the convert model API in OpenVino, which will convert the model to OpenVino model. And as part of this conversion process, it applies all the high-level graph optimizations that I just described behind the scenes. And optionally, we can save this model we can serialize and save this model. If we are using the same model again, like we can actually skip the conversion step and directly use the OpenVino IR that is pre-converted. And once the model is converted, then we compile the model to a specified hardware target, like GPU or NPU. And as part of this, like we can set a property called cachedir, which will allow us to also serialize and save the compiled models onto the disk. And when this property is set, when the inference is run for the first time, the model is compiled and exported, and it's saved in the cachedir that is provided by the user. And in the second time, in the subsequent inferences, this compiled object is detected and it's loaded automatically, and it's used to run the inference. So after the compilation is done, we can just provide the input data and get the result. So this allows us to save first token latency, which is quite significant in the generative AI applications. And beyond this, we also have several pipeline optimizations that we apply as part of OpenVino GenAI. So OpenVino GenAI is actually a high-performance library that we built on top of OpenVino runtime. And the primary path that we use to export the transformer models is via Optimum CLI export. And since today Hugging Face provides many of these models in PyTorch format, we support direct PyTorch conversion to OpenVino IR. But we are also looking into ONNX model support, exploring that as having that as an intermediate step, and also looking into supporting the ONNX models that are pre-exported or pre-optimized. And as part of this export process, we also apply optimizations like stateful transformation, and we use NNCF to quantize or compress the model. And then we hand it over to the OpenVino GenAI, which has a very easy-to-use pipeline APIs. It has APIs both in Python and C++ that the users can use. And when these pipeline APIs are used, we have several optimizations. For example, we have optimized tokenizers, where the tokenization operations are represented in OpenVino IR for performance improvements. And we also have support for single, multi-LoRa, and also dynamically merging different LoRa models. And we have many KV cache optimizations available, like in-place KV caching, prefix caching, KV cache compression, and many more. And we are also adopting features like page retention, continuous patching, speculative decoding from leading implementations like VLLM. And more recently, we added support for RAG pipelines and also support for structured outputs that can allow us to easily use the GenAI with Model Context Protocol and OpenAI APIs. So once these pipeline optimizations are applied, then OpenVino runtime can use the model optimizations at the model level, and we get the end-to-end optimizations. And next, actually, I will talk about a demo. I'll describe a demo that our colleague Garth pre-recorded for us. So that demo actually uses OpenVino GenAI for adventure gaming. In a typical adventure game, the game arena is not fixed. Typically, players create fictional characters that embark on adventures in a fantasy world. And in the adventure gaming, the players can describe the scenes that they want to play in, which makes it very exciting. So as part of that demo, Garth will actually use multiple models where the first model is actually voice activity detection and whisper transcription to detect whether the speaker is speaking, and also like to transcribe the speech. Then another LLM is used to parse that description and then produce a stable diffusion prompt, which is then used by a stable diffusion model to generate an image and upscale it with super resolution. And all of these models are running locally on the device without any other interaction other than just the voice interaction. So now let's roll the video.
I've hit start, and you can see that our voice activity detector is working, and so I'll go ahead and start describing the game. Characters find themselves outside a huge, magnificent house with blue lights that's covered by fog and believed to be haunted. Now on the right-hand side, you can see it's giving some information about the decisions that it's making. It detected there was a relevant scene and has started to generate the image. You can also see in the task manager that we've got activity on the NPU and as well as on the GPU. On the NPU, this is our whisper transcription as well as our large language model that's doing the summarization and basic understanding of what I'm saying. And then we have the GPU, which is actually running Stable Diffusion and running Super Resolution. Okay, so we enter a gloomy dark hall with a large piano. Hanging above the mantelpiece is a wood-framed portrait of the deceased family. Now again, I'm not interacting with the PC at all, it's just listening to what I'm saying, and it detected that I am now talking about the game again. So it created a new scene. We now move into a room which looks like an evil hunter's den. A fire burns in the stone fireplace. So again, on the right-hand side, you can see it's making decisions. It's decided that it does need to replace this current image, and it's creating a Stable Diffusion prompt and then going to generate the image. So as you can see, with our AI PC and generative AI, we now have the ability to visualize our adventures. We can combine speech-to-text, Stable Diffusion, Super Resolution, and large language models to assist the game leader in leading exciting campaigns, and they can all do it locally without the need of an internet connection. Thank you for your attention.
Okay, thank you. I'll now hand over the mic to Mayuresh.
Thank you. Thank you, Amni. Wow, wasn't that cool? Everything you saw over there ran without an internet connection. It ran on the local device. And as you can see on the right, it utilized GPU and NPU and run every inference on the device. The main thing that powers this is a stable format for a model, which actually helps you run on different devices. So a standard model like ONNX or OpenVino is able to let you just transfer your inference from one device to the other. So now let's talk about how we will run the ONNX model inference through ONNX runtime APIs. So if you are an ORT developers, if you have an ONNX model, there are few ways to get it into and run it on Intel devices. You can have a full precision ONNX model or a pre-quantized ONNX model, or as Yamini talked about, you can use neural network compression framework to actually quantize or compress the ONNX model. And all of this will be fed into the ONNX runtime. The main thing that happens is in the OVIR front end, which basically converts the model from ONNX representation to an OVIR representation, which is then compiled to the device that you have targeted. So whether it is a CPU, GPU, or NPU, or whether you can use Auto as the interface, which lets you choose the device at runtime in the backend. Basically, you just continue to provide the same model, use same APIs, and it runs across any of the devices underneath. So the main thing that ONNX runtime also provides is if there is any specific operators or ONNX operators that are not supported in OpenVino in the backend, you will have graph partitioning that happens, which means that unsupported operators will run on the CPU through MLAS plugin, versus all the operators which are supported, the subgraph will run through OpenVino execution provider on the targeted device of your choice. So there will be graph partitioning that would happen, and you will have the entire model running on the device with split graph running on CPU. So previously we had scenarios where a lot of optimizations were available with OpenVino, but there was a request to support some of these optimizations on the ORT API front as well. So now all these OpenVino optimizations and properties are exposed for ORT developers as well through OpenVino EP load config. So with that, you will be able to specify OpenVino configurations for ORT applications, and you will be able to run the same, again, ONNX model on Intel devices, but with configuring these properties through ORT APIs. We also worked on startup latency, which is one of the key aspects. Some of these models, especially as they grow larger, take a lot of time to compile. So we want to make sure that we compile only once, they cache that model onto the, once cache the compiled model and then save it onto the disk. Next time when you come in, you only utilize the cached model so that you don't have to go through the compilation process again. There are a couple of ways that you can cache the models for ORT applications. One is the ORT EP context. That essentially allows you to cache a model and save it in a application-controlled blob format. And the second one is OpenVino cache_dir. This is a framework-controlled caching. Yamini briefly talked about that as well. With ORT, you can choose either of these caching mechanisms based on whatever you prefer, whether it's the application that controls the blob or whether it's the framework that controls the blob. We also have a device selection, which is abstract, which means you just specify auto and the backend based on the device you are running on the platform you are running on, it makes the choice of the device which is best suited for the model. Or you have explicit direct plugins, which means you can target the specific CPU, GPU, or NPU, or you can even specify the device LUID and you will be able to run for that specific hardware. We have done several compile and runtime memory enhancements, which means that we try to minimize the number of copies of the models and the weights in memory so that you get minimum memory utilization. Also, in terms of weight management, which means we've tried to utilize or reutilize the weights and share them across original model as well as compiled model. We are also working on certain features which will allow you to utilize weights between different devices as well. So you can use the same weights across multiple different hardware devices. This is a code snippet which helps you show how you can run your ONNX models through ORT APIs on OVEP. First, you kind of set up the environment using setupvars.bat, which is a way to set up the OpenVino environment on the platform. Then you import ONNX runtime. And then the two key things that you essentially have to do over here is set the session options, which allows you, for example, if you want to do caching, that session options will let you select what is the directory where you want to actually save the cache to, whether you enable the cache, disable the cache. Those are all the settings available in session options. The next thing that you decide is the provider option. So provider option essentially lets you configure how do you run OpenVino AP, what device you run on, what's the precision you want to use. All of those are configurable parameters as part of OpenVino provider options. And then you initialize or create the session. Once you create the session, you pass in the model, you pass in the session option and provider option, and you just say you want to use OpenVino execution provider, and that's how you create a session. Following that, you only use run inference. Basically, session.run lets you pass in input data, and you will, per inference, you'll get your output data. That's how easy it is to run a model through ORT, through OVEP. So in summary, ONNX is infused across the stack. It's model optimization, where you can actually quantize or compress the model using an NCF. It's model inference, where you are actually running an optimized version of ONNX model through OpenVino or ONNX runtime framework APIs. ONNX models can also leverage features in OpenVino like model caching, auto, as well as runtime optimizations to run on all our devices, Intel CPUs, GPUs, or NPUs. So yeah, that's about it. Thank you so much.